Your next speaker is, oh, there we are. No, I'm on the right page. That's, oh, Menelaos Sarantos, migration rates of exospheric sodium and potassium from LADEE data.
Thank you, Mihai. I put up this beautiful picture of the sodium coronas observed from Earth, but I will talk exclusively, unless time permits, about potassium today, mainly because knowing its distribution on the surface simplifies greatly, helps us advance our interpretations from this unique LADEE data set. You've seen this measurements of sodium and potassium before. They were published 6 months ago in Science, and there were several trends that were identified. Assuming this is just a transient column abundance seen from the same vantage point near noon over the duration of the mission, you can see several trends. For instance, there were monthly trends every month. The exosphere for these two species appeared to be periodic. It was varying by about a factor of 2 systematically. There were also a smaller 25% sort of annual or semi-annual trend for sodium. There were clear correlations, increased brightness, increased emission observed during some of the showers at least, most notably Geminids. When you mapped this data set back to surface composition for potassium, it was shown there was shown to be very good correlation with the composition of potassium on the ground, as seen from lunar prospector, with the exception of these data points there that coincided with the Geminids meteor shower. For sodium, again, the issue is we don't know what it looks like on the surface. But it became evident that there was an apparent correlation with the shape of the mare. What we're trying to do here, at least today, I'm trying to answer 3 questions. There are many more, but the questions I would like to address today, given the potassium data, is what do these measurements tell us about the source processes for this species? Micrometeoroid impact vaporization, ion sputtering have been proposed to promote these neutrals into the atmosphere. A certain portion of it recycles, then photons can re-excite them multiple times. The second question, though, is, well, could photons directly excite and emit sodium from the mineral and glass without impacts having much to do with it, and therefore what we see during meteor showers is just a cherry on the cake, the icing on the cake. And finally, given these measurements, what are the sink processes? Where does this material go to? There's simply too many parameters, even for potassium, for which we know the main parameter, unknown for sodium, what's going on the surface. There's still so much to play with. The source rates are unknown. The temperatures of the source processes are unknown. So that's what we'll try to constrain with some models. The photodesorption cross section is somewhat measured from simple oxides on the laboratory, but not from lunar samples. So there's at least a factor of 4 uncertainty. So you can treat it as a free parameter within some constraints. The sink rates, again, is something that we can get from the evolution of the atmosphere following a meteor shower. And also, there's bound to be some fraction, at least, because at the small velocities of micrometeoroids, when they impact relatively small velocities, when they impact at the moon, a good fraction of the volume vaporized is actually due to the projectile itself. So there is an exogenous fraction which, as I will show, directly plays to the interpretation of the measurements here. So the models that I'll show later on, basically they can be summarized as the following. Every time you crank up the sink rates, if you lose the particle on its first contact with the surface, the amplitude of the observed monthly variation would be large. It would directly reflect the map of Chrysalis. And this is not what was observed. There was good correlation, but not a factor of 10 difference over a month. When you crank up the photo desorption rate, how many times you reuse the particle that was emitted previously, the amplitude of the monthly variation goes down. And so for source temperature increased, decreases, dilutes essentially the effect of the soil composition map. And last, by upping the fraction of exogenous versus endogenous vapor, you can also basically eliminate the composition map. So let's look at some models. But before that, what enables all this work is taking out one other big unknown, which was done here in Saleh et al., 2016. Basically, for the first time, Jamie and co-workers put together the observations by LDEX, and shown here in gray, and UVS, shown there in black. This was done for potassium in this particular figure. And whereas we couldn't make a clear correlation between the response of the atmosphere and the measurements by the dust counter, for other times, during Geminids, the residuals matched very well. And by fitting an analytical model, a simple ordinary differential equation model, you could find the drop-off, the sink rate, how long after the meteor shower, how long did it take for the atmosphere to subside after the meteor shower. And the inferred sink rate is essentially something between 6 to 8 days. So fixing this, assuming that this applies implicitly, that this sink rate applies to all soils and all times, we'll try to find self-consistent solutions with Monte Carlo models now between the monthly variation and the evolution of the atmosphere during a time-dependent event. So the pumping is periodic in this system because assuming impact vaporization to be the main process, which for some models also here would be the assumption. You have the influx of micrometeoroids, which are basically what the LDEX is saying, centered around 7 a.m. assumed here with a dawn-dusk asymmetry of a factor of 4. And then you convolve basically this influx with a rotating composition map, and that gives you the vapor that's produced from the soil. And of course, this essentially peaks, the instantaneous rate for such an atmosphere would peak when the creep soils are at 6 a.m. local time or 7 a.m. Let's assume in this set of models that we have a single source process. Impacts on these two top panels, 5,000 versus 2,000 Kelvin. It's uncertain what the impact vapor temperature is. It's within those limits. And then let's also assume a third model in which all the sodium comes off the mineral simply with photons. And impacts are, with the exception of meteor showers, a minor player. So what we can see here, the different lines now are different models that assume the same sink rate, which is a few days as inferred from Geminids, but show different photon-stimulated desorption efficiency, shorter residence times, if you wish, for particles that have recycled. And what you can see here is very quickly, there's a couple months of data from UVS over there. There is a little bit of variation. So as a function, lunar phase, what you can see right here is that if, for instance, the potassium that we observed in the atmosphere was directly emitted from the mineral via photon-stimulated desorption processes, the observed variation over a month would be too large. So that basically says that the direct photodesorption from glass is a minor component for potassium. What this models demonstrate is that basically you can best approximately match the observed magnitude of the monthly variation by assuming a hot impact process. You see that even a 2,000 Kelvin source overestimates the expected magnitude of variation. Now, neither of these two models essentially match the amplitude though very well. And that's partly because of the sink rate. So once you take as I said, the quicker you take previous ejections out of the simulation, the more you reflect the composition and inhomogeneity of potassium on the atmosphere now. So one way to mitigate this is to actually compute how much vapor is contributed by the projectiles themselves. And so if one assumes CI chondrites, they bear about 500 ppm, parts per million of potassium. Indeed, if one part in 3 of the total vapor is due to the vaporization of this component, this actually fills in what's going on at new moon. So it produces sort of the right amplitude for the monthly variation. So that's telling us that at least part of the vapor just doesn't see them up because the content of the chondrites is essentially comparable to or exceeds the potassium in the highland soils on the far side. Now, notice though that even though the general trend is okay predicted, there's about half the leg there that exhibits a different dependence in the data than can be reproduced in the model. One could assume that the transport parameters, so remember that all of this has been produced by assuming the same soil parameters for all soils. So my first assumption, my first thought was that, well, maybe the photodesorption cases, the photodesorption cross sections are different over those soils. But I think new work with other metals that Tony will present today shows the same trends that essentially over this longitudes you see similarly perturbed regions. So it must be the details of the impact vapor model, as shown by Jamie yesterday, because the ratio of the apex and helium and anti-helium components change over a month. This is something we haven't captured here, and this is probably what constitutes this discrepancy. So 2 more slides. Can we reproduce what we observed during examinids with this sort of model that sort of works for the monthly variation then? One thing that we didn't notice earlier on was not only did LDEX peak during the examinids by a factor of 2 essentially, but also there was one of the strongest solar wind events as seen by Artemis about 12 hours before the peak of the Geminids. So both impacts and sputtering essentially peaked within that Geminids window. So what were the implications for the exosphere? So one set of models shown here considers only impact vaporization. Forget about sputtering for a second. This shows that if you assume that the impact source was at 2000 Kelvin, because the radiant for this shower is at 2 a.m., you basically can put fresh particles on the day side soon enough. And so you wouldn't predict the jump at the right time. It would continue to rise long after the shower had ended. There's sort of a better fit if you assume hot vapor, 5000 Kelvin or more. So both lines of work, the amplitude of the monthly variation, as well as the response of the day side exosphere to an event that happened at night side and dawn, indicate very hot impact vapors as the drivers. This is the second set of models now that consider the effect of sputtering at various yields. And what you can see is if you assume about 8% yield during this event, you would have a considerable contribution by sputtering. You can see the data are shown here in red. There's a, what is it? I guess this. See, there's a factor of 2 decrease in the data in about like a couple of orbits. And that is single-handedly the peak of the sputtering event, which is not quite captured in the model as well. Anyway, this is still a lot of work to be done. The third question that I will address in just one slide is, so we're seeing very short sink rates. These are not the times that it takes for potassium to get to permanently shattered regions or to be lost via ionization in the atmosphere, given that it waits some finite time, several hours, before the next photon re-excites it. So how do we lose this much potassium so shortly? What this shows is the photodesorption rates, or the times between bounces, as something waits in the soil, and also the time it would take for a particle to migrate on the surface of the grain of a 10 micron grain there and a 70 micron grain there. So at temperatures around 300 Kelvin, all these particles, they can't desorb. They cannot thermally desorb because they're ionically bound, but they can travel a lot on a grain, jump to another grain, and so very quickly they're actually drawn away from the surface into the first 100 microns. And first diffusion model that we ran here for large grains, about 70 micron grains with some log normal distribution, does demonstrate that, regardless of the pre-exponential and the binding energies that you assume, you can draw these particles, protect them from light within the first microns. And now this is a long-term reservoir that you create with essentially inward diffusion. Reactions with oxygen would also be based on the same mechanism of a particle, a sodium or a potassium particle, hopping around the grain until it finds an oxygen which is not mobile. So, to summarize, two pieces of evidence demonstrate that impacts must be the main driver, and sporadic micrometeoroids must be the main driver for potassium. We couldn't prove it with the time sequences when we matched LDEX and UVS. There was really poor correlation outside of Geminids. But based on the expected source processes and the monthly amplitudes that they would create, I simply don't see any other way to only come up with a factor of 2 variation in the potassium atmosphere when we know so much more potassium exists over the creep soils. This is also consistent with, how do you see such a big brightness enhancement on the day side with something so heavy like potassium when the radiant of the shower, the Geminid shower, is at 2 a.m. So that again says, a very hot impact source, at least 5,000 Kelvin or on the other hand, what I missed explaining in the model is that in this model runs was that the source rate is underestimated. So somehow we come up with impact vaporization rates in the literature, we come up short of the measurement by factors of 2 to 4, depending on the adopted sink rate. So, that's telling us somehow we're vaporizing more potassium, perhaps, than expected. Or maybe it is that reservoir of adsorbate that's sitting, just below the reach of photons that can be re-excited when large micrometeoroid grains vaporize the soil. Last but not least, the particles are not lost through the air or to permanently shattered regions. They're lost to the subsurface. This is way too quick, a sink rate. They're lost to the subsoil and they just remain basically, they either react with oxygen, and that would explain why during jamming the sink rates might be increased actually, because we see a lot more oxygen with UVS during jamming, and some of that would return. But on the other hand, just inward diffusion, thermal migration on the surface of the grain would really create a huge reservoir. You wouldn't need for these species to go to the permanently shadowed regions to create a long-term memory, if you wish. Thank you.
Okay, thanks. So we're falling into great risk of, well, we will guaranteedly run into the next thing, which is Jim Green's NASA Town Hall, which will be going on